Good morning, this is Dr. Jingbo Louise Liu. Today we start chapter 6, the thermochemistry related to the energy flow and chemical change. We are going to cover 5 key topics in this chapter. First one, the form of the energy and their interconversion. The second one about enthalpy during the chemical changes, particularly at constant pressure, and then calorimetry to measure the heat transferred during a chemical or physical change. And then we show you the stoichiometry about the thermochemical equations. The last key point will be the Hess's law. We are going to learn how to find the delta H of any unknown reaction based on the known reactions. The last topic is related to the standard enthalpies of reaction. We are not going to further discuss them, but you need to know the delta H naught for your reaction. So it's the known value. You can calculate them from the delta H for the formation reactions. So first of all, let's clear off several important terminologies about the transfer and the interconversion of energy. So first of all, we need to know the thermodynamics. Thermodynamics is a study of the energy and its transformations of the matter during either physical or chemical changes, also involved in phase transition. Thermochemistry is a branch of thermodynamics. Thermochemistry is dealing with the heat involved in chemical and physical change for that particularly interested matter. When the energy is transferred from one object to another, the energy can occur as heat and work. Energy appears as work and heat during the transfer. There's another two important terminologies called system and its surrounding. The system is a group of interacting or interrelated entities that form a unified whole, so you call it system. The meaningful study of any transfer of energy requires that we first clear off the definition of system and surrounding. System and surrounding, they are equal to the universe. The universe is the sum of your system and the surrounding. In the next slide, I will show you the system and the surrounding one more time by an example. There is one more called internal energy, one more terminology called internal energy E. The internal energy E of a system is the sum of the potential and kinetic energy of the particles present. The total energy of the universe remains a constant value. The change in the energy of system must be accompanied by the equal or opposite change in the energy of your surrounding. Meaning, the energy change of the system is the same as the energy change of your surrounding, but have opposite sign. If your energy gains heat, or if your system gains heat, your surrounding must release heat. Also, we are going to show you several examples. So in this slide, you see a beaker, you see a Erlenmeyer flask, you see orange-colored solution, you see a Bunsen burner, and some other devices. So the system, to repeat, is the group of interacting or interrelated entities that form a unified whole. In this case, your system is what you are going to study. So in this case is your reaction Erlenmeyer flask and the aqueous solutions in this Erlenmeyer flask. Anything else surround this system, you call the surrounding. The surrounding compresses everything else. So including this beaker, this volumetric, volumetric flask, and the pH meters, and Bunsen burner, etc., etc. Again, the system in this case is the contents of the reaction flask, anything inside of this flask. So the system and your surrounding together composed of your universe. And then let's see some examples. For example, so if you have this energy diagram, so which can show you the transfer of internal energy between the system and its surroundings. So if you have the figure A, for example, figure A showed the system energy decreases. Initially, your system have higher internal energy. After the consumption, the energy decreases during the final state. Therefore, your energy is released from your system to the surrounding. Energy released to your surrounding. This delta E for your system is smaller than 0. Delta E equals E final minus E initial. Figure B. Energy of your system increases. So if you have your initial state, that initial energy is lower, final energy is higher. So the delta E again equals E final minus E initial. This delta E is bigger than 0, meaning your energy is going to be absorbed by your system from the surrounding. The last one actually have A and B as well. Essentially showed you the similar ideas about the energy transferred as a heat particularly. And then we also want to mention one more time your delta E, the energy change, internal energy change equals the E final minus E initial. If you have a chemical reaction, delta E equals the E products minus E reactants. That's how you are going to determine the energy changes. Also, I have a figure 4A, figure 6.4A and 6.4B. Both again showed you the energy is transferred as the form of heat. For example, if you have this system, in your system, so you are going to have some gases and some substances such as your zinc reacted with hydrochloric acid, produce hydrogen gases and the zinc chloride. In this case, you generated the gas. This gas is going to do the work to the surrounding. So again, this case, the internal energy change released as a form of work. We need to know the sign conventions of your heat, of your work, of your internal energy change, delta E. Delta E can be calculated by the Q plus W. Your Q, which is the heat, plus your W, work, equals to the internal energy change. So this Q and W, they have different signs, meaning if you have the plus sign for Q, the system gains heat. Positive is plus sign, meaning your system gains heat. Similarly, if you have your W, which is positive, meaning the work has been done onto the system. On the other hand, if you have negative sign meaning the system releases heat to the surrounding, loses heat. Therefore, you have a couple different possibilities. If both Q and W, they are positive, meaning gain heats, and the work has been done to your system, in this case, your internal energy will be positive, will be increased. On the other hand, if your system releases heat and your system has been done the work, so the internal energy will be negative, will be smaller at the final state. If you have positive Q, negative W, so your system gains heat and your system also does the work. In this case, your internal energy is going to be depending on the size of the Q and the W. On the other hand, if your Q is negative, your W is positive. So the internal energy change, the sign for the change will be also depending on the size, on the quantity of your Q and the W. Another important law is called the law of energy conservation. So you already learned it. It's also called the first law of thermodynamics. The law of energy conservation is also called the first law of thermodynamics. The first law of thermodynamics states the total energy of the universe is constant. Make sure the total energy of the universe is a constant value. The energy of the universe is conserved. The energy of the universe is neither created nor destroyed. The energy of the universe can be transferred in the form of heat and work, or either in the form of heat or work. The delta E for your universe, the energy change of your universe, equals to the energy change for your system plus the energy change for your surrounding. This value is 0. The delta E for your universe is 0. Couple minutes ago, we mentioned the system energy change and the surrounding energy change numerically are the same but have the opposite sign. They cancelled out. Your energy have different units. The SI unit, the international standard unit of your energy, is in joules. This is J, capital J, meaning joules. The joules is defined as 1 kilograms multiplied by 1 meter squared divided by 1 second squared. We also know the calorie. The calorie was once defined as the quantity of energy needed in order to raise your temperature of 1 grams of water by 1 Celsius. So that energy required is called calorie. 1 cal equals 4.184 joules. I also suggest try to remember this conversion number, 4.184 joules. There is another commonly used unit called BTU, British Thermal Unit. The British Thermal Unit is often used to read the appliances. 1 BTU equals to 1055 joules. Good morning, this is Dr. Jingbo Louise Liu again. Last time we stopped at this sample problem to determine the change in internal energy of a system. So our question is, so when this gasoline burns in your car engine, the heat released causes the products of carbon dioxide and water to expand. Therefore, these gases will push the pistons onward. The excess heat is removed by the car radiator. If the expanding gases, carbon dioxide and water steam, do work for 51 joules onto your pistons, and then the system releases 325 joules of heat to your surrounding. Calculate the energy change delta E in joules, kilojoules, and kilocalories. What's your plan? In order to solve these problems, we need to know how to define the system and the surrounding and assign the signs to your Q and W accurately. The equation delta E equals Q plus W is critical for you. Then you are going to convert the different units from joules to kilojoules, from kilojoules to kilocalories. So here is our solution. Step 1. Assign the sign for your Q and W. Because your heat is given out by a chemical reaction, so it makes sense to define the system as the reactants and products involved. The pistons, the radiators, and the rest of your car can't compromise the surroundings. If your heat is given out by the system, the Q will be negative. Your Q equals negative 325 joules. Because your gases expand to push the pistons, the system does work onto your surrounding. Therefore, your W also negative. W equals negative 451 joules. You simply apply the equation delta E equals Q plus W. Q, which is 324, which is in negative sign, and your work 451 also in negative sign. Totally, the delta E equals negative 776 joules. You are going to do the conversion. Convert joules to kilojoules. 1 kilojoules equals 1,000 joules. So our calculation is the internal energy change equals negative 0.776 kilojoules. Similarly, you convert kilojoules into kilocal. 1 kilocal equals 4.184 kilojoules. You are going to complete the conversion from kilojoules to kilocalories. That's your sample problems. Further on, we are going to understand the enthalpy. Enthalpy during a chemical change at constant pressure. As we mentioned, your delta E equals Q plus W. To determine delta E, both heat and work must be measured. Most common chemical reaction chemical work is P times V. You call it PV work. The work done when the volume of your system is changed in the presence of external pressure. Enthalpy, use capital H to denote it. You use capital H to denote your enthalpy. Enthalpy is defined as the sum of your E plus P and V. Therefore, the change in enthalpy equals to the change of internal energy plus the change of your P times V. If your system remains as a constant pressure, usually the volume change can be negligible. Your volume does not change too much. In this case, this delta P times V approximately equals to 0. Your delta H is essentially approximately equals to the delta E, but they have opposite sign. For example, if you have two different pathways for the energy change for your whole system. The first one, you assume you have your gasoline. Gasoline can be combusted in the air. Therefore, the product, carbon dioxide and water, can be formed. In this case, your E is going to be released as the heat. As the heat, you heat it up. We call this exothermic reaction, as you just calculated in your first question. And then the E can be also released as work. So your car has been moving, your piston has been up and down, up and down. So even though your Q and W are the two pathways, these two pathways, they are different. Therefore, the total delta E will be the sum of both, keeps constant. Another case is your gas expanding. The expanding gas pushing back the atmosphere. So you have the P times V. Your W equals negative P times delta V. So your delta H usually is used as a measure of delta E. Delta H is a change in heat for your system at a constant pressure. So most of the cases, your delta H equals the delta E plus P times delta V, because your P is constant. And your QP equals delta H. Delta H, as we mentioned, can be approximately as your delta E under several conditions. Number one, if your reaction do not involve in gas, this P times delta V is 0. Point 2, if your reaction which totally involved in the gas, but the number of moles of your gas do not change, meaning your reactants and products have the same total number of moles. In this case, delta H is approximately the same as your delta E. For your reaction in which the QP, this heat, is much larger than P times delta V. In this case, even though your total moles of your gases will be changed, however, can be negligible. So your delta H is approximately the same as your delta E. How do you determine this delta H sign? So in other words, how do you know the reaction is exothermic or endothermic? So we have this determination. If your delta H is smaller than 0, meaning final H is smaller than initial enthalpy, in this case, your heat is released out to the surrounding. This is your exothermic process. On the other hand, imagine you have a solid water. It's going to be melted under regular condition. So this delta H is bigger than 0. Delta H has a positive sign, meaning your heat will be giving in to your system. This processing is called endothermic. In short, exothermic process, meaning the heat is giving out. Endothermic process, meaning the heat is taken in, absorbed. So let's try to draw the enthalpy diagram, and then we are going to determine the sign of your delta H. So we have two different reactions. The reactions showed you where the heat is. So here is our plan. So you need to understand where the heat is. Is the heat as a reactant or a product? If your heat is taken in as a reactant, the heat taken in as a reactant, this process is endothermic. If your heat is released as a product, for example in A, this process is exothermic. exothermic. For the enthalpy diagram, the arrow always pointed from the reactants to the products. The endothermic, meaning for your endothermic, the products are higher in terms of energy than its reactant energy, because your reactant takes in heat from your product. Let's see, for example, the first one, your hydrogen and oxygen, they reacted with each other, that's your reactant, and then you produce water, liquid, and your delta H. In this case, so you have your hydrogen and oxygen, which is your reactant, your water product, and your delta H as your final product. In this case, your delta H will be negative. When the delta H is assigned as a product, delta H has a negative sign. This chemical reaction is an exothermic. The second example, B. So your heat has been taken in as reactant. The heat taken in as reactant meaning your heat plus your H2O in liquid produce gas. In this case, so you have the heat which is positive in sign. This processing is an endothermic. The very last point will be the calorimetry. So we have this technique, analytical method, in order to determine the heat transferred during either physical changes or chemical reaction. The Q represents the heat either gained or lost. This Q equals C times M times delta T. Your C represents specific heat capacity. Your M represents the mass of your substance in grams. Delta T equals the T final minus T initial. This delta T can be in Celsius or in Kelvin. They are the same. The temperature change in Kelvin and temperature change in Celsius are the same because that 273 cancelled out. Our example, if you have a layer of copper welded to the bottom of a skillet with 125 grams, your copper with 125 grams, how much heat is needed to raise the temperature of the copper from 25 to 300 Celsius? Assume the heat capacity for your copper is 0.387 joules per gram per Kelvin. What's your plan? The plan is, number one, determine the mass. You know the mass, you measured it, and you know the heat capacity. And then you need to find the delta T using T final minus T initial. And then you use your Q equals C times M times delta T to calculate the heat. Yes, our solution. Delta T equals to T final minus T initial. So meaning 300 minus 25 equals to 75, either in Celsius or in K. So in this case, because 300 plus 273, 25 plus 273, that 273.15 has been cancelled out. So and then you use your Q. Simply replace all the numbers into your equation. So my calculation is 1.33 times 10 to the power 4 joules. There are a couple other calculations about the stoichiometry of your thermodynamics. We are going to further study it in next class in your 6B. Thank you so much. You have a beautiful day.